All right, so today's lesson, last lesson of week, oh my goodness, what are we on? 35, 36, 70? Who knows? Is to calculate and solve with inverse variation. So you might remember we've done direct variation earlier. Now we're going to do inverse or opposite. Make sure that you've gotten these notes either printed out or set up in your notebook. Then you've got the homework down in your planner. So as always, when we introduce some new vocabulary, we're going to define that first. So this is the opposite of direct variation. So if you recall, we can put the notes down here, is that direct variation or proportional variation could be written as y divided by x equals k, some constant. So the opposite of this would be then y times x is equal to some constant, because multiplication is the inverse or opposite of division. And this k here is a constant, and it's sometimes called the constant of variation. And you can see it written like this, and then sometimes we like to put the y by itself or the f of x by itself. So you divide that x over, and you can have the function also written as y is equal to k over x. You'll use it both ways. They both have different applications. It's not going to make that much of a difference since we're just learning about this for the first time. So let's do some problems with this new type of variation. Write the function given x and y vary inversely, and when x is equal to 2, y is equal to 3. So in order to write the function, all we need to do is replace this k value, because we leave x and y there when we write our functions. And so if we're given the function y times x is equal to k, we know our x and y values, so we can just substitute them in. Y is equal to 3 times 2 is equal to k. So now we realize that 6 is equal to k. And since we leave the x and y as they are, our function then is x, y, or yx. Don't know why I wrote it in that opposite order. And now we're left with yx is equal to 6. Which would be a lovely way to write it, but if you wanted to use the other way, you could also say y is equal to 6 over x using either one of these two formats. Now, as you've noticed before, we've talked a lot about graphing the function. So if the function in number 1 again is that y times x is equal to 6, we're already given one point, which is that when x is equal to 2, y is 3. So that's the point right here. But with only one point, that's not going to give us a lot of data. So we're going to put a lot more on this graph. When it comes to multiplying by 6, you can think about groups of factors. So since we know that 2 and 3 multiply to 6, so do 3 and 2, 1 and 6, 6 and 1. These are all good points here, and it starts to give us a nice picture of the shape of this graph here and here. So we're going to have this curve. And here's another important thing, just like the last lesson, is you'll notice it's getting flatter as it goes this way. We're also going to have asymptotes here, because if you think about it, let's say we want to plug in 0. Well, that tells us that y times 0 equals 6, which is impossible. You can't actually do that. So this is a DNE problem, which is a sign that there's going to be an asymptote at x equals 0. X equals 0, also known as the y-axis. We have an asymptote here. And by the same logic, if y is equal to 0, 0 times something equals 6, that also won't exist. So then you also have an asymptote here. Remember, that means that the graph can't cross. So when I'm drawing my graph, I get kind of close to the x-axis and the y-axis. going through those points, but I'm never actually allowed to cross it. So we have both vertical and horizontal asymptotes here. Now, unlike exponential, we are allowed to put in negative numbers. If I have -1 and I want to multiply to 6, that's just a -6. The two negatives cancel out. So then I have this point here. Same with -2 and -3, -3, -2, and then -6, -1. So we have a nice symmetric graph here. Again, not crossing those asymptotes. So all of your inverse variation graphs will look like this. The main thing will be if it's a super steep curve like this or something that's a little bit slower like that. It's just going to depend on that constant of variation there. But they're all going to have these two asymptotes here and here, because you can't multiply a number here with 0 and expect to get a non-zero term. We also have things in our day-to-day lives that have this type of variation. One example is that the frequency of a guitar string changes inversely with its diameter, meaning that the higher the note is, the thinner the string is. So a C string vibrates at 32. The unit is abbreviated Hz. It's pronounced hertz. And its diameter is 0.03 millimeters. So then what is the diameter of a string that vibrates at 50 hertz to create the note G? So we see here it says that frequency varies inversely with diameter. So something that might be helpful is, instead of thinking about them just in terms of x and y, is to think those are your variables. So you can write it as frequency times diameter, instead of just x times y or y times x, is equal to some k, because that's what it means to vary inversely. So just like in number 1, the first thing we want to do is find this constant of variation. Given our first two, we have numbers to plug in for frequency and diameter. We can say that the frequency is 32 times the diameter, which is 0.03, is equal to k, giving us 0.96 is equal to our constant of variation. So now, once we've done that, we can then ask, what's the diameter if we know the frequency? Using this same function here, frequency times diameter is equal to k, we can say frequency in our new problem is 50, the diameter is our unknown, and k we can plug in from here and say is equal to 0.9, I almost wrote 296. Divide both sides by 50, and you end up with the diameter d is equal to 0.0192. We use the units from earlier where frequency was hertz, so then the diameter also has to have the same unit, which is millimeters. So our final answer, the diameter is 0.0192 millimeters. If it asks you to round in the problem, of course, follow that example. Let me know if you have any questions in the comments below, or you can come stop by in Zoom or on Google Classroom.